Hello, welcome back to tutorial number 9 for the linear algebra course at AOU, specifically chapter 3, where we talk about vectors, spaces, subspaces, span, bases, and dimensions. In this tutorial number 9, we will talk about section 3.1, which specifically talks about vector spaces. We'll start off with some definitions about vector spaces and their properties. A real vector space is a set of elements V together with two operations, addition and multiplication, satisfying the following properties. Notice please here that we have special symbols for the addition and multiplication. These are reserved specifically for addition and multiplication of vectors in vector spaces, which are different from the normal symbol that we know for addition and multiplication of real numbers. Therefore, for every vector u, v, and w in the vector space V, we have u plus v in V. Therefore, any two vectors, when we add them together, the output or the outcome must be in V. What we can say here is that V is closed under addition. Also, we have u plus v is equal to v plus u, which means that addition is commutative. Also, we have u plus v plus w is equal to u plus v plus w. Therefore, addition also is associative. There is an element 0 in V, in the vector space V, such that u plus this element 0 equal to the element 0 plus u, which is equal to u. And for every vector u in V, there is the negative of this vector minus u in V, such that u plus minus u equal to minus u plus u is equal to 0. Also, for every u v in V, every two vectors u v in the vector space V, and for any two real numbers r and s in R, we have r times u in V. In other words, the vector space V is closed under scalar multiplication. Also, r times u plus v is equal to ru plus rv. R plus s times u is equal to r times u plus s times u. R times s times u is equal to r times s times u. Finally, 1 times u is equal to u. Following are some examples of vector spaces. The set V, which is equal to Rn, together with the standard operations of addition and multiplication by a scalar, is a vector space. The set V of all matrices m by n with the operation of matrix addition and scalar multiplication is a vector space. Finally, the set V equal to Pn of all polynomials of degree at most n together with the polynomial addition and multiplication by a scalar is a vector space. Let's look at some examples how we handle vector spaces. Example: show that the set V, vector space V, which is equal to xy, vector, any vector xy, such that x is greater than y, where x and y belong to R, together with the standard operations of vector addition and multiplication by a scalar in R2, is not a vector space. In other words, we have to show that this vector space here that has this rule is not a vector space by referring to the properties that we have seen before. If we take a specific example here, let x equal to 5, 3, where as you see 5 is greater than 3, therefore this satisfies the rules for the vector space V. But when we multiply this vector x by a negative scalar value minus 2, which belongs to R, minus 2x is equal to minus 10 minus 6, and minus 10 is not greater than minus 6, therefore this violates the rule, and therefore this vector space is not a vector space. This vector V is not a vector space. Example number 2, show that the set V equal to R3 together with the standard operations of vector addition and scalar multiplication in R3 is not a vector space. The rules for this particular set V is if we have two vectors x, y, z and x prime, y prime, z prime, we note that the rule is as follows. It's not a normal addition of two vectors. x is equal to x plus this vector plus this vector. We have here x plus y prime, here y plus z prime, and lastly z plus x prime. And if you do multiplication by a real number, we have r times x, y, z, rx, ry, rz. Let's take an example to show whether this is a vector space or not. If x is equal to 1, 2, 0 and y equal 3, 6, 7, and both of these vectors belong to V in R3. Now, if this vector space, if this set is a vector space, then x plus y must be equal to y plus x. But we note here, as per the rule, that x plus y is equal to 7, 9, 3, whereas y plus x is equal to 5, 6, 8. And since the outcomes of both of these operations are not equal, therefore the addition in this vector under the rule is not commutative, and therefore the set V is not a vector space. Another example here show that the set V equal to R3 together with the standard operations of vector addition and scalar multiplication in R3 is not a vector space. For this reason again, but we note before we address this or answer this question, note that the multiplication here is a specific one here. R times x, y, z, the first element here becomes rx, here becomes ry, but when we multiply this times this, we obtain a 0. Let's see if we take a particular case. If x equal 1, 2, 3, where x belongs to the set V. If we have 1 times x, if we take 1 times x, normally 1 times x must be equal to x. But in our case, following the rule here, 1 times x becomes 1, 2, and 0, which is different than x. And this violates the last rule that we have seen in the properties of vector spaces. Therefore, the conclusion here is that this set V is not a vector space. This ends this tutorial 9. I hope you can benefit from it. Good luck.